Hello everyone, welcome to the part A of this tutorial video titled Introduction to Freedom Application Programming Interface, the FAPI. I am Amiya Haque, a PhD student at NC State University working in Freedom System Center. Me and my colleague CA will cover this tutorial video. At first, I will give an overview of how we have designed this video. Then I will introduce you all to the FAPI, its purpose, how an external developer can access it, how the code sharing works, and the framework development. I will finish this video with an overview of how the hardware and the hardware in the loop setup looks like. Let's see how we have divided this tutorial. In part A of this video, I will introduce you all to the FAPI. I will cover its purpose, explain how the external developers can access it, and describe the development process of the framework. Additionally, I will provide an overview of the hardware and the hardware in the loop setup. In part B, the video will guide you through a step-by-step tutorial on how to use the FAPI. Now let's discuss the FAPI. FAPI is a specific application programming interface developed at the Freedom System Center, which is designed to streamline the grid farming controller development process. To assist UNIFI integration and validation area and the control area deliverables, NCSU has started the development of a grid farming controller validation, assessment, and implementation framework from concept to hardware. FAPI consists of three main stages as specified in this section: the software in the loop, that is the seal, the control hardware in the loop, that is the C-hill, and the physical hardware testbed. The figure shows variants of FAPI for each development stages. The external application block in the figure represents the external developer's GFM control that needs to be implemented and evaluated. The code repository can be compiled and used in both seal and the hill environments. In both cases, it offers automated mechanisms for application development by external developers. This framework supports seamless code integration across seal, C-hill, and the hardware stages. It comes with fault write-through, transient condition emulation, and secondary control interface options. It has multi-rate control and seamless integration with external GFM controllers. FAPI supports both white box and black box controller sharing for the purpose of collaboration. This framework includes pre-compiled libraries and templates for user-defined controller integration. The FAPI framework provides the external developers, that is the UNIFI members, the opportunity to implement and evaluate custom controllers without needing to concern with lower-level firmware. The core goal to this framework is to enable external developers to test and deploy their grid farming control algorithms. The key feature is to provide a framework for GFM controls validation that is compatible with NCSU Typhoon hardware in the loop setup and multi-inverter hardware testbed. This serves both for the validation and implementation of the NCSU grid farming controller with fault write-through features, as well as for enabling other UNIFI members to implement and validate their code using the NCSU TI DSP based Hill and VSI hardware. As the name implies, the test setup already have a comprehensive base firmware that includes protection, state machine for handling startup, shutdown, etc., and optional core control. The purpose of this FAPI framework is to provide the external developer an offline simulation environment which has been set up to mirror our Hill and hardware setup. To access these test facilities, an external developer will need to use the FAPI. The external developer can develop their grid farming control that may or may not include a current controller, and they can utilize the current controller in the base firmware if needed. The developer needs to verify first that their control functions properly in the offline simulation. If an external developer wants to use the FAPI, they will request access for the FAPI Git repository. Then they will receive the template application and the dynamic link library builder tool. The framework provides them static and dynamic library builder tools so that they can share their code as black box with us. Developers do not need to manage the DSP peripherals like ADC, PWM, or handle state machines startup shutdown. These functionalities are managed by the FAPI framework of the code, which resides in either the DLL file or the for the seal or the static library for the C Hill or the hardware development environment. The FAPI package will come with pre-compiled black box dynamic linked library, that's the .dll file in seal environment, and the static library, that's the .lib file for DSP target in HIL environment. In addition, example wrapper files template is also included. During development stage, an external developer needs to follow the template to integrate their controller. Automated mechanism to include multiple external applications in the same build allows the user to choose applications to run, allowing the comparison of different grid farming controllers. The external application wrapper comes with three files. The first one is the fapi.h, which provides set of data structures and function prototypes for the FAPI-based external application modules that will be integrated with the FAPI library. The second one is the FAPI wrapper app external one.h. This is the header file for the FAPI wrapper app external one.c, which externalizes FAPI feedback and command input and reference output pointers. The third one is the FAPI wrapper app external one.c, which is the main wrapper file for external applications. External developer needs to specify a function definition that corresponds to its application. All these files will be explained in details in part B of this video. For an external developer who are external to NCSU, to use this framework to validate their code, the code can either be white box or black box. An external developer may share their source code to the Freedom team as white box, then it will be fully transparent. Then the NC State team can validate it for the developer using this framework. Alternatively, an external developer may generate static library, that's the .lib, from their source code using the TI Code Composer Studio project template, which is included into the FAPI repository, to generate the .lib file for the hardware or the hill setup target, and then use the DLL builder tool, which is also included in the FAPI repository, to generate the .dll for the SIL target. After the external developer completes offline simulation verification using Plex, the NCSU Freedom team will conduct the hill and hardware testing and communicate the results with the developer. Now let's talk about the framework development. In this SIL environment, Plex model consists of several components: the power stage, the command and reference panel, feedback of sensing signals, FAPI seal wrapper model, and the plots. As it is shown in the figure, FAPI based SIL wrapper is a C script block in Plex which links other components from Plex model with external C codes as well as the FAPI dynamic link library. FAPI library takes care of the functionalities of the firmware layer, including interrupt generation, protection, PWM, and sensing. It also accepts reference commands and passes them to the software layer, which is designed to accommodate user defined grid farming models. In the Plex based SIL model, FAPI is included as single dynamic link library, and external control software can be included as white box and as many header and source files as the user desires. FAPI based SIL model can be used by an external developer to verify their code in a single converter infinite bus setup. Multiple instances of the seal wrapper can be used in the same Plex model. FAPI-based control hardware in the loop development environment utilizes the Typhoon Hill 604 real-time simulator. The model schematic in Typhoon Hill Control Center is shown in Figure 4, which consists of our power stage and the grid. Command and references will be handled through the CAN GUI SCADA. In addition, Hill is configured to send feedback and power setpoint reference as analog output to the TI C2000 DSP. An external developer who wants to test a novel GFM controller can use the Code Composer Studio project to integrate and load control code in TI DSP Launchpad mounted on the HIL TI microgrid Launchpad interface. FAPI is included as static library in TI Code Composer Studio project alongside the user-defined GFM control as either a black box static library or white box C codes. Prior to start Hill simulation, CCS project code needs to be loaded to DSP. During runtime, user-defined GFM control sends reference to FAPI. FAPI generates PWM signal from DSP and actuates the switches or power stages. Identical wrapper file is used for SIL and the real-time control hardware target, so no additional effort is needed in this case. Pure hardware testbed environment for the grid farming controlled inverter adopts the same software control code as C-Hill and SIL development environments when FAPI framework is used. The difference in sensor types, as in the ADC for Hill setup or the SDFM for the hardware, command and reference interface will be taken care of by the FAPI library. The external developer or the user-defined GFM control software part will stay identical regardless of the development environment. Similar to the control hardware in the loop environment, the Code Composer Studio project with black box external control software, the .lib, and the FAPI static library that can be integrated and loaded to the TI DSP residing on the NCSU three-phase VSI hardware. Now let's talk a little bit about how we do this CAN-based SCADA. A CAN-based SCADA interface is used for both the HIL and hardware test benches. Operational commands like run or stop, control mode, etc., and the references are dispatched from the SCADA. The disk GUI provides the status and the terminal quantities monitoring. All the control parameters are exposed to the user on the SCADA in readable or writable form. Now I will show you how the hardware and the hardware in the loop setup looks like. This is the physical NCSU three-phase VSI hardware setup with all its components. It includes the three-phase GFM inverter, the energy storage, the three-phase grid emulator, and the resistive loads and chokes. This is the setup for the Typhoon Hill. We can see that the Typhoon Hill 604 being used in this experiment along with its scope outputs. All the TI DSPs are mounted on the Hill TI microgrid interface boards. And we finished the introduction to the FAPI. Thank you so much for your patience. If you have any questions, feel free to reach out to us. Check out the part V of this video, which will guide you through a step-by-step tutorial on how to use this framework.
Hello everyone, welcome to this video. My name is Siye and I am a student from NC State University Freedom System Center. This video is part of the demo or tutorial for the FAPI framework, which is designed to facilitate GFM control development. So in this video, we will go over what you need to prepare to use FAPI, give an overview of what's in the FAPI package, a breakdown of the steps how to use FAPI for GFM control development with example, and then demonstrate how to use it with software in the loop setup in the Plex environment. So first we will just mention some keyword that we will be using in the rest of this video. First is FAPI framework. It stands for Freedom Application Programming Interface. It is a tool developed and provided by the NCSU team to streamline concept to hardware design and implementation of novel inverter controls in 3 different setups using the exact same control codes. First environment is a Plex-based software in the loop environment. And second is a hardware in the loop setup with Typhoon real-time simulator and TI DSP. And third and last setup is the fully programmable hardware inverter prototype located in the Freedom Lab. And another term that we will be using extensively is external application. So essentially here it means the novel control GFM control software that is to be developed by the external partners or partners from UNIFI consortium using the FAPI framework provided by NC State team. And we will look at an example of what it may look like later in this video. So next, we can talk about preparation and what the user need on their computer or laptop in order to use the FAPI framework. And in the workflow of the proposed FAPI framework, just a little bit of the background. The first step is for an external application developer to get access to the GitHub repository or the FAPI package in a zip file form. And in this video, we will first discuss in detail different parts of the package inside the GitHub repo. And then we will show how we start to build and validate controllers using FAPI in software in the loop environment. When controller is successfully verified in SIL, then the developer may share their external application with NC State team as a white box or black box in the form of a static library file. For black box sharing, NC State team will provide a Code Composer Studio project template, which will help the user to compile their external application code as a black box. Then that can be tested in the Hill environment here in the Freedom Lab. And if that goes well, we can also run it on our hardware testbed. So yeah, as we just mentioned, then the first requirement is for the user to clone or download the FAPI package from GitHub repo to their local computer. And then step 2, it is required for the user to have or to download and install Microsoft Visual Studio on their computer, and it can be a community edition. And the third requirement is to have a Plex standalone simulation platform on the user's end. And then optionally, the user can use any code editor. And for this demo, we will be using VS Code Editor. Let us have an overview of what is inside the FAPI package. When the user downloads or clones the FAPI package from GitHub repo, the first thing they will see is a top-level folder named Development Environment. So this folder contains a CCS project that has a target configuration and all the TI header and source files that allows the external application GFM control algorithm to be deployed to a control hardware. In this case, it's a C2000 DSP from the TI. And then it is used both in the Hill as well as a pure hardware setup. Then there's a folder named FAPI. So this folder contains the static library for the FAPI package and the files with all the data structure of the FAPI interface is named fapi.h. And it also provides a set of wrapper header and source files. Also, one example of how external application setup can be done is included here as well. So these wrapper files wraps around external application code and act as a abstraction or interface layer that interacts with the FAPI firmware, which lives in the .lib file, as well as those external application control code we will see that lives inside this file named external app. Right now it contains an exemplary GFM code, and later on the user will replace these with their custom made GFM codes. All right, and then the last folder here is named MRC_seal. This folder contains a Plex model of a three-phase VSI with some initialization files. It also contains the DLL builder to include external application C code, source, and header files to generate a dynamic link library that can be used by the Plex-based seal model. And then this entire folder is excluded from the CCS project, which is designed for the Typhoon Hill environment. All right, then once the dynamic linked library is built, it will live inside this build folder. Right now, as we can see, it's empty. And later in this video, we will take a look how to generate that dynamic linked library. The internal FAPI software lives inside the .lib file, include modules such as EPWM code, ADC code, protection code, as well as all the other lower level firmware that is to be used in the DSP, as well as the seal environment. As external application developer, we want to have an interface to those data structures that lives inside the static library file. And so this interface is defined in FAPI.h. So if we think about what an inverter control needs, it needs a voltage and current feedback. In addition, for GFM control, it will need frequency reference, voltage command, and reactive power set point. FAPI provides the sensor feedbacks and the commands as input to external application. In this case, it's a user-defined GFM controller. And the external application then uses these inputs, runs the control update, and feedback the current or voltage reference back to the FAPI, which is again lives in the .lib file. And then here notice FAPI actually provides two options. One is the current mode and another is the voltage mode. In current mode, external application controller only generates the current reference and then sends it back to FAPI. FAPI has an internal current controller which takes care of generating the modulation voltage reference that is going into the PWM module. Or in mode 2, external application may include its own current controller and then sends that output directly back to the FAPI. Therefore, in this case, modulation voltage reference is directly sent back to the FAPI framework. Let's take a closer look at this FAPI.h file. First, we define a set of data structures. Here, X and Y means stationary frame signals alpha and beta. FAPI vector S_T means stationary frame vector with X and Y component being alpha and beta components. Then we also have FAPI vector SS_T. This means symmetrical stationary vectors. It has a positive sequence and a negative sequence component. Then we have an enumeration with external application ID. We can conceive a scenario there are multiple types of GFM controllers implemented as FAPI app external 2 and 3 within the same software build. Right now, in this repo, we just have one external application example, and it is named after FAPI app external one. And then we already discussed that external application can generate current or voltage reference. In FAPI reference out mode underscore T, we are defining the options that one can take. Then FAPI also provide the operating limit of the inverter that one need to consider when using it. That is defined here in the S constraint T. Limit constraints include the current limit, real and reactive power limit. We need to note here that the external application example that is provided in the repository or the package that comes with FAPI does not use all these limits. It is a baseline GFM control, and if you run it under default, it will fail. We also have here the feedback inputs, FAPI feedback input underscore S. Grid current and voltage feedbacks are what the controller will need. SIO and SVO of type vector S underscore T are stationary frame vectors. This means that we are getting current and voltage feedbacks as stationary frame signals. SIO or stationary output current feedback, and SVO or the output line-to-line voltage feedback from the grid side. In addition, FAPI software, which lives in the static library file, already decomposes the grid voltage and current feedbacks into positive and negative sequence component, and they are also feedback as SSIO and SSVOs from this interface. And users are welcome to use these feedback signals as well as they are already available in this data structure. Then here we have a set of command and reference values. They are provided through a structure called FAPI S command input under T underscore T. That includes real and reactive power reference, voltage, and frequency reference. So up until this point, FAPI constraint, FAPI feedback input, and FAPI command inputs are all the signals that comes from the FAPI as input signals to the external application. One should only read these values to update their control, but not to write to these data structures specifically. After the control update, external application has to write and load the reference output to the data structure FAPI reference output underscore T. And the first element here is the stationary reference vector voltage or current based on the mode selection. And then the second element is W, which resembles the frequency. And if we are doing the GFM control, it is generating the effective internal frequency reference, and that should be loaded into this W. And the third element is the angle, reference angle theta, and this is optional and it can be used for debug purposes. Towards the bottom of this file, we can also see the exported variable declarations of the data structures we just mentioned, so that it can be used by the external application developer in their codes. Besides the above 4 data structures we just discussed, the rest of this file also contains some other data structure that are internally used by the FAPI, and it's because it's fully automated, the external application developer do not need to worry about those other signals. And an additional thing here is that under SIL wrapper environment, we also have access to FAPI debug input and debug output signals. We will go into how that might be used later on in this demo video. So now that we understand what the data structure looks like for on the interface for the FAPI, the next step in the workflow is to use the FAPI wrapper files to link the external application to FAPI software. For that, we will look at this file named FAPI wrapper app external1.c. So there are four important things in this file. So to begin with, we have access to the global variables, which are of the data type defined in FAPI.h in the form of a pointer. Then we have four things. First, initialize function, reset function, then there's control update function at TS rate as well as 1 millisecond rate. To begin with, for any power electronics or inverter control that we do, first thing we need to initialize the control states. For instance, any of the PR, PI controllers, low pass filter. In this case, for the external application, all of those tasks needs to go under void initialize. If we take a close look at the comment here, that it specifies exactly where the custom code needs to be. Do not edit above and below these two lines. And selection of the control mode also happens here. As we discussed, it could be either a voltage mode or current mode. After the mode selection, whatever code one needs to initialize external application can go here. In this template, this is empty, and we will see how it actually looks like with the example later. This initialization function takes an input of TS. This is the sample period that is sent by the FAPI to the user. So since the controller is implemented in Z domain or discrete time domain, we need to know the actual sample or the control update rate in the DSP. And that information is available to the external application from the input of this initialization function. The next thing that external application has to take care of is the reset function. To understand what needs to go into the reset function, so there are two objectives for this. When running the inverter, we can send signals to turn the inverter on and off by a start-stop signal, let's say. During the operative state, controller is running. All the low-pass filter, droop controller, angle integrator are all updating at its corresponding control update rate. It could be a TS rate or a slower timescale 1 millisecond rate. In the event when the inverter goes from operative mode to inactive mode, or when it's disconnected from the grid, the update of these control elements stops and the states are stopped at a arbitrary value. However, in this condition, the DSP, the control hardware is still on. It still has the power. And then we can imagine the scenario when the angle integrator of the droop is integrating at the frequency, and it stops at, let's say, an angle of pi over 3. And then when we want to turn the inverter back on, and the grid voltage may be at a completely different angle. In this case, there will be a huge spike in the current, and that will cause the inverter to trip for the protection to kick in. So what goes into this function is to reset all the state that needs to be reset every time before we start the controller for the inverter to enter operative mode. That means that the reset function is called exactly once by the FAPI before the external application control starts to work again, so that the inverter entering the operating mode. So one example of what needs to be reset is the angle that needs to match by the angle from the measured grid voltage feedback. The next function is update underscore TS. So this function is the principal control update function. It contains all the control update activity at sampling frequency. At every sample period of TS, external application controller updates all of its components, including PI, PR, low pass filter, current controller, etc. So everything that needs to be updated at TS rate will come here. And then the next one is update underscore millisecond. So one key characteristic of FAPI framework is that it enables a multi-rate control update, in particular when there are timescale separation in the controller, for example, with faster inner loop, current voltage loop, and the rather slower primary control, droop control. Not all of the control action needs to be done in the fastest control update rate, which is the TS. So this is helpful to save some computational resources. As an example, let's say the voltage controller needs to be quite fast, but the droop controller bandwidth is quite slow. Here, then the droop controller does not need to be exist in the update underscore TS function. Instead, it can come here in update 1 millisecond. And this way, computations related to the droop control will only be updated every 1 millisecond. It is not a mandatory. You can still put droop control update inside the update TS function here, as long as there are enough computational resources available. And an example of how wrapper file is used is given in this FAPI wrapper app external example.c file. So everything in this file is identical to the FAPI wrapper app external one.c. Besides that, what goes between the line says do not edit and below this line. Here inside the initialize function, a external app function named AC initialize is called. So what is being sent into this function is the sampling frequency TS set by the FAPI, and then these pointers to the FAPI command and feedback input, as well as the reference output. Then in the reset function, AC reset is added, and AC update TS and AC update 1 millisecond functions are added to the TS rate and 1 millisecond rate update functions. So basically, these 4 lines are the only edits that external application developer needs to do in the wrapper template files. These AC update, AC reset, and AC initialize functions are defined in the external application code base. And that example code located in the external app folder. This folder contains only the example code for an external application. And it's not part of the FAPI framework, so just to keep that in mind. For any external developer, they can bring their own control code into this subfolder to replace all of these exemplary files here. So in this tutorial, we will not look into the details of what the example code is doing, but just to get an idea of how it looks like, we can look at the definition of AC initialize function. So as we can see, it lives in AC control.c, which is under external app subfolder. So here in AC initialize, first the address of the input from FAPI are being copied into a local data structure AC data. So that is the internal to the external application so that we can use it later in this file. And then there goes the init droop control, and then init first order filter for virtual admittance implementation. Notice here, because in this example, we want to demonstrate how to use multi-rate control. And the last input for this init droop control is the to period for the to control update. First is the period for reference update. We can look at to see this is the slower 1 millisecond update. And then there's the period for the TS rate update. And then in the reset function, reset droop and the reset of the virtual admittance first order filter is called. And if we go into the definition of the reset droop, we can see that the stationary frame grid voltage feedback is used to obtain magnitude and angle by Cartesian to polar transformation. And then the angle is loaded to the theta of the droop control structure. Similarly, control update tasks are implemented in AC update TS and AC update 1 millisecond correspondingly. Code Composer Studio links the FAPI static library file with the FAPI wrapper files where the functions from external application code is being called. And because the code containing these AC external app functions lives under this subfolder named exe_app, the CCS can automatically find it and then create a .out file that can be loaded to the DSP. And this is the original build for the Hill setup. A similar build exists for the hardware setup that we have in the Freedom System Lab, with a slight difference in how the sensor signals are processed from the FAPI side. So the integration of external application to both SIL and HIL are done at the same time using the FAPI framework and the wrapper file. So we will just quickly do that. We copy everything from the example wrapper file to the actual wrapper file that will be used by the FAPI framework. Next, we will just show how the exact same external application code is used in the Plex SIL environment. If we again bring up this file, everything related to SIL setup is inside this mrc_sil folder, and then Plex model is inside the PLX subfolder. Dynamic link library, again, will be located underneath this build folder. Now if we open up the Plex model for the three-phase inverter, on the left-hand side is the command and reference window, which a similar version of this exists in a CAN-based SCADA if we are using the Hill or hardware setup. And for the command, there is a start-stop signal, and then there's the control mode selection between FAPI internal GFL mode or the GFM mode that runs the external application control code. And if you're using the GFL mode provided by the FAPI, there are also two control modes, which can be a current mode or a PQ reference mode. Then in the reference, ID and IQ command can be sent if we are running for GFL current control mode. And for the PQ reference and voltage frequency reference, that can be sent by the user for the GFM control mode. And external application is will be taking these as the input. and users can play around with different reference and set point values to get different nominal operating points. And feedbacks and plot are more or less straightforward. Feedbacks takes the measurement from the power stage subblock, and then plot just plots the measurement signals and potentially the debug signals. If we look under the power stage, we can see on the left there's a average model of the three-phase bridge. Essentially, it is a purely average model with an additional that a switch that is enabled by the PWM. Essentially, what this additional diode bridge element is doing is that it represents the behavior of the hardware when the PWM gating signals are disabled. And when the PWM is enabled, obviously it is just the average model itself. Let's close that. The next thing on the left is the ACLFL filter. And it's a simple three-phase filter. First meter is located on the converter side. So this is sending the current feedback to the FAPI. Then the next thing in this power stage is the AC main contactor labeled MX. It is between the terminal of the inverter and the AC grid. And then the second set of measurement meter is located on the side of the contactor. This meter sends back the grid voltage feedback to the FAPI. And on the rightmost is the ideal grid model with an RL impedance. All right, coming back on the top level, we see that these measurement signals are being selected through the feedback block as VIC and VGLL and sending to the C script SIL wrapper block. Now we can zoom into the top right box. This is the SIL wrapper, which is a C script block from the Plex. This C script block loads a dynamic link library DLL file internally. And this is built using the FAPI software and external application code that we previously incorporated through the FAPI wrapper files. On the input side, it is getting feedback signal VIC, VGLL, line-to-line voltage on the grid side, and then the VDC from the DC source. It is also getting command and reference signals from that panel on the left side. And then there's a trip zone placeholder being passed in here. Right now, this is not being used in any meaningful way, and in the future, we might be able to emulate PWM trip zone of the TI DSP here in the seal environment. Then there's a debug input signal. We will talk about that together with the debug output signals later on. Towards the end here, there's a disable protection option only for the seal environment. Now, when this is set to 1, FAPI software will not trip an inverter in the simulation when there are over voltage or over current problems. This is very useful during the development stage when someone is starting to develop the control software. If the software trips due to the protection in simulation, just like it is doing in the hardware, then the developer will not be able to debug the controller as it does not continue to run. Disabling this protection will allow the user to see the behavior of the controller so he or she can understand when and why the controller is tripping and not behaving as expected. On the output side of the seal wrapper are the task flags, gating signals, PWM enabling signal, and the main contactor signals and debug output generated by the FAPI. Debug out is where one can get an internal software signal out to the Plex model and then probably plot it on the scope to view how it is performing. Debug signals are a useful feature of this wrapper block. So for the debug input signal, we can send any arbitrary signal that are not part of the feedback reference or command to the controller. And the maximum number of 16 signals are kept in provision. And for the output, the total number of signal kept in provision is 32. Just to demonstrate how to use the debug signals, we have included one arbitrary sine wave as the debug input in the provided Plex model. As we can see here, a sine wave is getting passed as the first element of the debug signal, which is sent directly into the SIL wrapper. And for the external application to get that, again, we looked into this ACC control.c file. It is reading the FAPI debug input 0, which is the first element in the debug input, and pass that directly to the first element of the debug output signal. In addition to that, we are also passing the controller internal frequency and the voltage value AC data GFM.W and .V to the second and third element of the debug output so that we can look at those in the Plex scope. Okay, let's now come back to the Plex model. We can recall that this SIL wrapper block requires a DLL or dynamic link library to run. It is configured to look for the DLL file inside this underneath MRC SIL Plex build directory. So right now we don't see any of the DLL files here. So next we will take a look at how we build the DLL. To do that, we actually will need Microsoft Visual Studio to build the DLL automatically using this build DLL application. There are two parts to prepare for the DLL build. First of all, Visual Studio needs to be installed on the user's computer. And second, we will make sure that the MS build path is added to the path environment variable. So what do I mean by the second step? We can go into the following directory, which is this PCC program files. If we look for Microsoft Visual Studio, then we go into MS Build, Current, and Bin. Here we will see an application called MS Build. This is the application that we will use to build the DLL. To do this, the path of this application needs to be in the system path. To add that, we go to Edit, System, Edit, System in Environment Variables, and then Environment Variables. Underneath the lower tab, we will see a variable named Path. Double-click to add this, create new entry. Actually, first to copy this directory of the MS build, then create new entry, paste, click OK, then OK again, OK again. Now, if we go back to our FAPI external repo directory under MRC SIL, there is let's open this application. This is where we will add all the external applications, include and source folders. First is the include directory for all the header files. We will browse, then select folder for the exe_app, click add. Then we need to add all the source folders one by one. Open, add, open, add, the last one, add. Now that we have included all the header and source files from ext_app folder, we click modify the project. We see the message that project file successfully created. Click OK. Then build project. Build completed successfully. Click OK. After this step, we should be able to see the DLL file under mrc_sil, plex, and then build. Now they have shown up here. So now we are ready to run the plex model with the external application control code. So if we go into the plex model, select mode of external app 1, start the simulation. Then we looked into the operating inverter. So this waveform, we can show a successful operation of the inverter with the external application code. Furthermore, we can look into the other scope where we are plotting the debug signals. So as we remember, arbitrary sign signals is passing in as the debug input, and then we are getting that exact same signal out from the debug output. Similarly, we are having the internal frequency and voltage passed out to the debug output. And with that, I'm going to conclude this video. To summarize, first, we talked about different parts of the FAPI package in the repo. Then we demonstrated how to build dynamic link library to use the FAPI framework with an example of external application code for control verification in Plex environment. For users of FAPI, if Plex verifications of the controller is successful, the next step is to build a black box static library for their own external app control software. NC State team can assist with providing a CCS project template for building that black box static library. After that, NC State team can test their external GFM control software in a Typhoon Hill environment and in a pure hardware silicon carbide based inverter in the FREEDM lab. Thank you.